This is a historical map from 1595. Three things should instantly stand out to you: Saya de Malha, Baixos de St. Miguel, and Baixos de Chagos. What exactly are these three geometric abnormalities doing just beneath the surface of the Indian Ocean in 1595? Stick around and find out. This is the Saya de Malha Bank, the largest non-natural formation on Earth. Saya de Malha is located in the Indian Ocean and is part of a submerged oceanic plateau, the Masarene Plateau. Saya de Malha is approximately 1,000 kilometers northeast of Madagascar and about 800 kilometers southeast of the Seychelles Islands. Saya de Malha is situated between latitudes 8 and 12 degrees south and longitude 60 and 64 degrees east. The Masarene Plateau also includes the Masarene Islands as well as other submerged banks like the Nazareth Banks and the shoals off St. Brandon. The Chagos Archipelago is roughly 1,750 kilometers northeast of Saya de Malha. I posit that Saya de Malha is of man-made origin and that before 1500 this area was above water. But before I lay out my evidence, let's talk about marine hazard and identification so we are all operating on the same shared context. This map of the Indian Ocean was authored by Jan Huygen van Linschoten in 1595. Areas like these represent a shallow area that may pose a hazard to seabound travel. A reef, shoal, gravel bar, bank, some sort of continuously submerged area that is visible from the surface. Individually marked crosses like these indicate a rock or other underwater structure or hazard that is dangerous to navigation. Generally, objects marked with an X will also be more of a threat during low tide. Now, to be clear, our boy Jan here is not a minor figure in history, and he did not just randomly squiggle lines on a piece of paper and call it a map. Jan Huygen van Linschoten was a pivotal figure in the age of exploration. Born in 1563 in Haarlem, Netherlands. His book Itinerario from 1596 broke the Portuguese and Spanish monopoly on the Asian trade by revealing key maritime routes and navigation secrets. His first-hand experience in Portuguese colonies gave him access to closely guarded data on winds, currents, and coastal landmarks. This knowledge laid the foundation for the Dutch and English East India Companies, transforming global trade and geopolitics. Linschoten's maps and writings became crucial resources for future explorers. His maps and writings were seen as reliable due to his first-hand experiences in Asia and his access to closely guarded Portuguese navigational data. With that established, let us take a closer look at his map, keeping in mind that if he drew something on a map, it was accurate to his observations. When I first saw this map a year and a half ago, three areas instantly jumped out at me: Saya de Malha, Baixos de St. Miguel, and Baixos de Chagos. All three of which are clearly non-natural formations. Why do I say that? Well, let's start with Chagos. This structure here, just beneath the ocean surface in 1595, is a near-perfect circle with two clearly non-natural openings that align west and north. To be clear, based on its shape and size, this structure is at least 40,000 square kilometers, almost 29,000 square miles. That is roughly the size of Switzerland. Not only are you looking at one near-perfect circle on the outside of the structure, the internal section is uniform in size. Notice how the internal structures are aligned with the uniform space between them and the outside structure. The internal structures are also clearly non-natural. Each structure is a near-perfect geometric shape. Circle, triangle, square, and rectangle, and other complex geometric shapes. Had a good look? Let us watch this structure degrade over 217 years, from 1595 until 1812. The Chagos Archipelago is fascinating. Unfortunately, I have been unable to discover any research papers that discuss the area and the bathymetry. But that is okay, because Saya de Malha is equally as perplexing, and I have far more than just maps to talk about when it comes to Saya. Before we head over there, let us analyze and discuss some of the maps we just saw. 1611, Isaac Pontanus. Chagos still has its distinctive circular shape and the opening to the north. 1700, Neptune Francois. The same circular shape still exists, as does the opening to the north. 1747, Pierre de Haan. Chagos is still roughly the same circular shape, but you are starting to see heavy degradation of the structure, though Pierre was still able to distinguish the internal structures 152 years later. 1776, Clout Montaire. Same circular shape, but even more degraded, but the internal structures are still visible. 1812, Aaron Arrowsmith. The circular shape is gone, as are the internal structures. Unfortunately, I've been unable to discover any maps of this area post-1812. Making our way towards Saya de Malha, we will take a brief stop off at Baixos de St. Miguel. There are 7 objects aligned in a perfect circle atop this perfectly circular bank, and there is a central object located directly in the center of those 7 objects. Now look at Baixos de St. Miguel in relation to Saya de Malha. 7 objects aligned in a perfect circle, nested atop a perfect circle, directly above such a distinctly non-natural geometric shape. On to the main event, Saya de Malha. Saya de Malha is clearly a geometric abnormality. This shape does not happen naturally. Don't believe me? Here is a mirror image taken from the right side of the structure. When it comes to land-based formations, nature does not work in mirror images of itself, especially underwater in the middle of an ocean when you are dealing with currents and tides. Next, note the 22 lines protruding out of Saya. Each line has between 5 to 7 triangle markers extending out from the main structure. If you remember from the start of this video, that indicates a continuously submerged area. Notice how each of these continuously submerged areas extends out exactly opposite from the area on the other side, whether horizontally or vertically. Pay specific attention to the uniform space between each of these submerged areas and the uniform angles in comparison to the opposite side of Saya. This is not natural. Don't believe me? Here's another mirror image to prove it. Additionally, the curved nature of each of these areas provides a 3-dimensional characteristic, seemingly denoting height and direction. When the points of these areas are connected, this becomes much easier to see and the uniformity stands out. As with Chagos, the sheer size of this area is mind-boggling. Saya de Malha is also the size of Switzerland, approximately 40,000 square kilometers. As we did with Chagos, let us watch this structure degrade over the next 217 years. Now, let's take some time to analyze and discuss some of the maps we just saw. 1635, Jean Bleu. Note the rounded curves and the symmetry of the structure, and how Baixos de St. Miguel is still perfectly above Saya. Is still a perfect circle, and those same 7 objects are arranged around a central object. 1667, Piedregos. This is 72 years later, and there are some big changes happening. First, notice how the distinctive Y shape is gone. Second, the bank of Baixos de St. Miguel is all but gone, but the central object is still on that bank. One would logically assume that this indicates that the central object was at a slightly higher elevation than the surrounding objects. 1684, Pierre Duval. This is our second major change. Notice the loss of shape in the lower section of the Y. This is 89 years after Jan's map, which clearly showed a rounded bottom. 1767, Jacques-Nicolas Belin. This is the third major change. Baixos de St. Miguel is all but gone, and Saya has completely lost its Y shape. Notice the 3 oval shapes in the lower section of Saya, each of which is nearly identical in size and shape. This indicates that something is either protruding up from or dipping into the structure. Additionally, notice how the depth indicators on the lower right and lower left sections of Saya are the exact same, 17, as well as the recurrent depths of 30 and 20 around Saya. Back in 1767, this Switzerland-sized mass was nearly flat. These maps are clearly intriguing, but what does all of this mean? Well, by studying the same area of the Indian Ocean over a time period of 217 years, we can clearly see how submerged structures degrade in this region and how quickly that degradation occurs. From 1595 to 1812, both Chagos and Saya are barely recognizable as the same structures. Given that it took 89 years from 1595 to 1684 for Saya to lose its distinctive Y shape and cease resembling its original shape, it is safe to conclude that either 1. Saya and Chagos were submerged approximately 89 years before the 1595 map was created, or 2. Saya and Chagos' original shape and size were even more distinctive and they degraded into what the 1595 map indicates. Look, I'm not saying I found Lemuria, but if this isn't enough to pique your curiosity, you're crazier than I am. So if you are still on the fence, strap in for part 2, an expedition to Saya de Malha from 2002. So, you don't believe that Noah's Ark was real? Well, these 6 maps, authored by English, Jewish, Venetian, Italian, and German cartographers from 1280 to 1587 say otherwise. Each map shows Noah's Ark in the exact same place, perched atop Mount Ararat in Turkey. I guess they were all just lying or making stuff up because they were bored, right? In March of 2002, the Lighthouse Foundation in Hamburg funded an exploratory expedition to the Saya de Malha Bank. This expedition aimed to assess the region's unique flora and fauna, construct a coral ark, evaluate the ecological significance of the area, and document the relatively unknown ecosystem. This expedition was crewed by experts in their fields, and we need to talk about them to understand the significance of their observations and findings. Professor Wolf Hilberts, first to formulate cybertecture and the inventor of mineral accretion technology, MAT. Mineral accretion technology is a sustainable method for promoting coral reef restoration and marine habitat growth. Thomas Garreau, world-famous coral biologist and pioneer in coral restoration. Frank Gutz, architect. Gabriel Despain, dive coordinator. Stephen Evans, specialist in geographical information systems and 3D computer modeling. GIS is a technology used for capturing and displaying spatial and geographic data. GIS enables the visualization of data in map form. It allows users to identify patterns, relationships, and trends across different locations. GIS is widely used in fields like urban planning, environmental management, and disaster response to support decision-making by integrating data layers such as terrain, population, land use, and infrastructure. GIS helps understanding geographical contexts and solving complex spatial problems. Not only is Stephen Evans a specialist in GIS, he holds a bachelor's in geography, a master's in engineering, and a master's in geography. He is a research fellow at the Center for Advanced Spatial Analysis, and he is a former cartographer with the British Antarctic Survey. This guy is the real deal, a true multidisciplinary expert with highly specialized understanding of geography and cartography. Legit, this guy is my hero. Peter Garreau, geophysicist. A geophysicist studies the physical properties of the Earth and its surrounding environment, applying principles from physics to understand how the Earth behaves. This field includes a wide range of topics such as earthquakes and seismology, magnetism and gravity, plate tectonics and hydrology. And for the sake of brevity, we are going to tip our hats to the remaining researchers and thank them for all of their hard work, but move right on because we are already at 13 minutes. Here's a little background on Saya. Isn't it interesting that it was named by Portuguese sailors 500 years ago? Here's a top-down map of Saya. Prior to 1997, there were no direct studies of the Saya de Malha Bank. In 2000, a couple crew members from this expedition went to Saya. They were unable to dive, but they took some video. Now, on to some observations. In the crew's own words, the predominant impression gained from visual observations sailing over the banks, diving on the bottom, and sonar tracks taken from our 2 expeditions is of extraordinary flatness. Although he found some areas as shallow as 10 meters, most of the area studied was very flat and about 15 meters deep. En route to Saya, the expedition found a huge submerged plateau on the northern side of the bank at depth of 70 meters, of even more extreme flatness. For hours, the depth shown on the sonar did not vary by more than a meter. Such large and extremely flat areas, lying at distinct levels, is highly unusual in marine geology, and their origin is uncertain. To be clear, these 2 guys here, a GIS specialist and geophysicist, have just said that the extreme flatness of the area is highly unusual, and they do not understand why it is like that. Here's a cute little 3D image of Saya de Malha showing you just how extremely flat it is. Here we go, talking about some maps. The GIS specialist and former cartographer says that these and other early map sources should not be overlooked when surveying an area like Saya de Malha, despite the fact that in the last few hundred years, many different techniques have been employed when mapping reefs, as both technology, the scale, and the purpose for which the map is required have developed and changed. This is particularly important to note since, although many older surveys were constrained by the mapping techniques available, they still offer an important data source for many remote parts of the ocean. Here's a cute little map showing their survey site. The results. The results largely display what many participants observed whilst on site, namely that the area surveyed was extremely flat with a few small-scale variations. Here's a three-dimensional visualization of their survey site. Note the extraordinary flatness. Although the analysis has shown that the area is largely flat, it has shown that there may be some interesting changes in the bathymetry, approximately 1 kilometer to the northeast of the main site. The Saya banks are two shallow plateaus, some 40,000 kilometers in extent, lying at the midpoint of the Masarine Ridge, a long mountain chain that connects the Seychelles banks to Mauritius. The banks are situated at a flexure point or bend. These studies show, through backtracking the plate tectonic movements, that Saya de Malha and the Chagos banks were originally a single feature that were later divided when a mid-ocean ridge opened up between them and pushed them apart. Here's a three-dimensional image of the seafloor around Saya. So, here's where things get really interesting. Over these next few pages, the crew begins to discuss the various possibilities as to why Saya de Malha is so flat. The banks on the Masarine Ridge are generally thought to be platforms made up by the accumulation of calcium carbonate limestone overlying an igneous rock basement of unknown type or depth. However, they differ from most carbonate banks in several striking ways. Deep-sea carbonate sediments are usually made up of the remains of planktonic microorganisms with limestone shells, primarily deep-sea oozes or algae. But these deep-sea oozes drape over the underlying formations and follow their topography, unless they have filled in low-lying basins and produced a flat surface. This is clearly not the case with Saya, which is a topographic high, which is unlikely to have been produced by a straight vertical uplift or an impounded basin. Normally, limestone banks are atolls produced by the growth of coral reefs around the edges of a subsiding volcanic formation, but this produces a bowl-like topography, not the flat horizontal surfaces seen on Saya. Normally, flat horizontal plateaus like Saya are produced only by erosion. If so, one would expect to find old rock formations at the surface that have been clearly eroded flat to a well-defined base level related to sea level at the time of formation. If Saya were primarily constructional and built by corals, it should show clear high topographic rings related to the primary wind directions, but this seems weakly developed. The third possibility is that the banks are built up by encrusting calcareous red algae, which usually grows in waters that are too deep, too rough, too cold, or too rich in nutrients for coral growth. But flat horizontal growth is extremely unusual and unlikely, given that their growth responds to gradients in light, nutrients, and wave energy. Our field observations suggest that these banks are largely constructed by calcareous red algae. To find out more about the nature and origin of the bottom, we took a drill core in a representative seagrass area. The uppermost few centimeters were sampled before the drill core hit a rubble-filled cavity. What's that? A rubble-filled cavity. Taking the length of the core, which measures 40 millimeters, and dividing it by the difference in age of the two samples, which is 500 years, the growth rate is 0.08 millimeters per year. This gives a rough idea of growth rates of limestone in this area. To summarize, in 2002, limestone had been forming on Saya de Malha for 500 years. This means that whatever was underneath the limestone must have been above water before that. If it had been underwater, limestone would have started forming sooner. Circling back to where we started, Jan Huygen van Linschoten's 1595 map of the Indian Ocean. We know when this map was authored, 1595. Through other maps, we have clear observational data that provides a rough timeline for the erosion of Chagos and Saya de Malha, roughly 89 years, from 1595 to 1684, for both areas to become nearly indistinguishable from regular banks and coves. We also have expert testimony that states, at numerous times, that the area is of extreme and extraordinary flatness, that historic maps should not be ignored as they hold valuable data, and that there were numerous abnormalities, bumps and blips on their echo sounder in areas that should not have been changing depths in the ways that they were. These experts also provided various hypotheses as to how the flat horizontal plateaus were produced, each of which was stated to be highly unlikely. We also have the presence of a rubble-filled cavity that somehow evaded the researchers' curiosity. How exactly did limestone grow uniformly atop a rubble-filled cavity? To grow, the calcareous red algae that eventually turns to limestone requires a hard surface to bore into, but in the drill core image you can clearly see that there's a gap between the rubble and the base of the limestone. I argue that this supports my hypothesis that Saya de Malha is of man-made origin and that pre-1500 this structure was above water. Why do I say that? Well, let me break out my master paint skills to illustrate that. Here you have a Switzerland-sized structure with a hard roof or ceiling. Imagine something like granite, marble, limestone, even wood. Something that limestone-producing red algae latched onto and began growing on top of once the structure was submerged. Over time, faced with strong currents and tides in the area, whatever that structure was would collapse and its contents would begin to degrade, filling the inside cavity. Once fully submerged, red algae latches onto the flat roof and the process of lithification begins. Over time, various seagrasses also begin to form on top of the submerged structure. It is quite unfortunate that they did not continue to drill because I am certain that beneath that rubble is a level, man-made floor. In summary, the heavily credentialed multidisciplinary authors state that this extraordinary flat limestone has been growing for approximately 500 years. Date of expedition, 2002. Date of Jan Huygen's map, 1595. That is a difference of 407 years. It took 89 years for the structures seen in the 1595 map to degrade to a nearly indistinguishable point. 407 plus 89 equals 496 years. Therefore, according to the core drill sample and simple mathematics, Saya de Malha was above water in or just before 1506, supporting my hypothesis. If only we had a map of the Indian Ocean pre-1500 to corroborate this hypothesis. Oh wait, we do? Let's take a look at Fra Mauro's map of the world from 1450. This map is beautiful, and the detail is exquisite. You could spend months analyzing this map pixel by pixel. I know because I have. But let's skip all that for now and just zoom in east of Madagascar. And a quick rotation. In this one screenshot of the east coast of Madagascar, you can see 15 villages, towns, and cities that are now completely underwater. Zooming back out, let's take a look at the Chagos area. And another quick rotation. In this screenshot, just south of India, you can see 18 villages, towns, and cities along with one large Colosseum-shaped building in the Chagos area. In this exploration of Saya de Malha and the Chagos Archipelago, we have uncovered compelling evidence suggesting that these massive formations, each spanning approximately 40,000 square kilometers, were not only above water before 1500, but likely of man-made origin. Through historical maps, expert testimony, and geological studies, we have traced the rapid degradation of these unique formations and highlighted their extraordinary flatness, which defies all natural explanations. The patterns we have observed in these maps, along with the remnants of megalithic structures, raise intriguing questions about our understanding of human history and geography. Did these areas once support thriving communities that are now lost to the depths of the ocean? I think I've shown some pretty compelling evidence to suggest yes. This video represents the accumulation of a year and a half of dedicated research and analysis, during which time I devoted all of my free time to exploring this topic, so I'd like to give a shout out to my girlfriend for listening to me talk about this stuff for a year and a half. Along the way, I delved into numerous rabbit holes driven by the discrepancies between what we've been taught about our history and the compelling evidence found in credible historical documents. My name is Kendall, and I sincerely thank you for spending 23 minutes of your busy day with me. If you enjoyed this journey, I would greatly appreciate your support through a like, a subscription, and by sharing this video. In my next video, we will explore the Bay of the West.